In computer science, the clique problem refers to any of the problems related to finding particular complete subgraphs in a graph, i.e., sets of elements where each pair of elements is connected. For example, the maximum clique problem arises in the following real-world setting. Consider a social network, where the graph's vertices represent people, and the graph's edges represent mutual acquaintance. To find a largest subset of people who all know each other, one can systematically inspect all subsets. A process that is too time-consuming to be practical for social networks comprising more than a few dozen people. Although this brute force search can be improved by more efficient algorithms, all of these algorithms take exponential time to solve the problem. Therefore, much of the theory about the clique problem is devoted to identifying special types of graph that admit more efficient algorithms, or to establishing the computational difficulty of the general problem in various models of computation. Along with its applications in social networks, the clique problem also has many applications in bioinformatics and computational chemistry. Clique problems include finding a maximum clique, finding a maximum weight clique in a weighted graph, listing all maximal cliques, solving the decision problem of testing whether a graph contains a clique larger than a given size. These problems are all hard. The clique decision problem is NP-complete. The problem of finding the maximum clique is both fixed parameter intractable and hard to approximate, and listing all maximal cliques may require exponential time as there exist graphs with exponentially many maximal cliques. Nevertheless, there are algorithms for these problems that run in exponential time or that handle certain more specialized input graphs in polynomial time. History. Although complete subgraphs have been studied for longer in mathematics, the term clique and the problem of algorithmically listing cliques both come from the social sciences, where complete subgraphs are used to model social cliques, groups of people who all know each other. The clique terminology comes from Luce and Perry, and the first algorithm for solving the clique problem is that of Harry and Ross, who were motivated by the sociological application. Since the work of Harry and Ross, many others have devised algorithms for various versions of the clique problem. In the 1970s, researchers began studying these algorithms from the point of view of worst-case analysis. See, for instance, Tarjan and Trojanowski. An early work on the worst-case complexity of the maximum clique problem. Also in the 1970s, beginning with the work of Cook and Kopp, researchers began finding mathematical justification for the perceived difficulty of the clique problem in the theory of NP-completeness and related intractability results. In the 1990s, a breakthrough series of papers beginning with Feiger et al., and reported at the time in major newspapers, showed that it is not even possible to approximate the problem accurately and efficiently. Definitions. An undirected graph is formed by a finite set of vertices and a set of unordered pairs of vertices, which are called edges. By convention, in algorithm analysis, the number of vertices in the graph is denoted by n and the number of edges is denoted by m. A clique in a graph G is a complete subgraph of G, that is, it is a subset S of the vertices such that every two vertices in S are connected by an edge in G. A maximal clique is a clique to which no more vertices can be added. A maximum clique is a clique that includes the largest possible number of vertices, and the clique number omega is the number of vertices in a maximum clique of G. Several closely related clique finding problems have been studied. In the maximum clique problem, the input is an undirected graph, and the output is a maximum clique in the graph. If there are multiple maximum cliques, only one need be output. In the weighted maximum clique problem, the input is an undirected graph with weights on its vertices and the output is a clique with maximum total weight. The maximum clique problem is the special case in which all weights are equal. In the maximal clique listing problem, the input is an undirected graph, and the output is a list of all its maximal cliques. The maximum clique problem may be solved using as a subroutine an algorithm for the maximal clique listing problem, because the maximum clique must be included among all the maximal cliques. In the k-clique problem, the input is an undirected graph and a number k, and the output is a clique of size k if one exists. In the clique decision problem, the input is an undirected graph and a number k, and the output is a Boolean value, true if the graph contains a k-clique, and false otherwise. The first four of these problems are all important in practical applications. The clique decision problem is not, but is necessary in order to apply the theory of NP-completeness to clique finding problems. The clique problem and the independent set problem of complementary. A clique in G is an independent set in the complement graph of G and vice versa. Therefore, many computational results may be applied equally well to either problem, and some research papers do not clearly distinguish between the two problems. However, the two problems have different properties when applied to restricted families of graphs. For instance, the clique problem may be solved in polynomial time for planar graphs, while the independent set problem remains NP-hard on planar graphs. Algorithms. Maximal versus maximum. A maximal clique, sometimes called inclusion maximal, is a clique that is not included in a larger clique. Note, therefore, that every clique is contained in a maximal clique. Maximal cliques can be very small. A graph may contain a non-maximal clique with many vertices and a separate clique of size 2 which is maximal. While a maximum clique is necessarily maximal, the converse does not hold. There are some types of graphs in which every maximal clique is maximum, but other graphs have maximal cliques that are not maximum. Finding a maximal clique is straightforward. Starting with an arbitrary clique, grow the current clique one vertex at a time by iterating over the graph's remaining vertices, adding a vertex if it is connected to each vertex in the current clique, and discarding it otherwise. This algorithm runs in linear time. Because of the ease of finding maximal cliques, and their potential small size, more attention has been given to the much harder algorithmic problem of finding a maximum or otherwise large clique than has been given to the problem of finding a single maximal clique. Cliques of fixed size. A brute force algorithm to test whether a graph G contains a k-vertex clique, and to find any such clique that it contains, is to examine each subgraph with k vertices and check to see whether it forms a clique. This algorithm takes time. There are O subgraphs to check, each of which has O edges whose presence in G needs to be checked. Thus, the problem may be solved in polynomial time whenever k is a fixed constant, when k is part of the input to the problem. However, the time is exponential. The simplest non-trivial case of the clique finding problem is finding a triangle in a graph, or equivalently determining whether the graph is triangle-free. In a graph with m edges, there may be at most theta triangles. The worst case occurs when G is itself a clique. Therefore, algorithms for listing all triangles must take at least omega time in the worst case, and algorithms are known that match this time bound. For instance, Chiba and Nishizaki describe an algorithm that sorts the vertices in order from highest degree to lowest and then iterates through each vertex V in the sorted list, looking for triangles that include V and do not include any previous vertex in the list. To do so, the algorithm marks all neighbors of V, searches through all edges incident to a neighbor of V, outputting a triangle for every edge that has 2 marked endpoints, and then removes the marks and deletes V from the graph. As the authors show, the time for this algorithm is proportional to the arboricity of the graph times the number of edges, which is O. Since the arboricity is at most O, this algorithm runs in time O. More generally, all k-vertex cliques can be listed by a similar algorithm that takes time proportional to the number of edges times the nd power of the arboricity. If one desires only a single triangle, or an assurance that the graph is triangle-free, faster algorithms are possible. As ITAI and Roeder observe, the graph contains a triangle if and only if its adjacency matrix and the square of the adjacency matrix contain non-zero entries in the same cell. Therefore, fast matrix multiplication techniques such as the Coppersmith-Winograd algorithm can be applied to find triangles in time O, which may be faster than O for sufficiently dense graphs. Alon, Yuster and Zwick have improved the O algorithm for finding triangles to O by using fast matrix multiplication. This idea of using fast matrix multiplication to find triangles has also been extended to problems of finding k-cliques for larger values of k. Listing all maximal cliques by a result of Moon and Moser, any n-vertex graph has at most 3 maximal cliques. The Bronner-Kerbosch algorithm is a recursive backtracking procedure of Bronner-Kerbosch that augments a candidate clique by considering one vertex at a time, either adding it to the candidate clique or to a set of excluded vertices that cannot be in the clique but must have some non-neighbor in the eventual clique. Variants of this algorithm can be shown to have worst-case running time O. Therefore, this provides a worst-case optimal solution to the problem of listing all maximal independent sets. Further, the Bronner-Kerbosch algorithm has been widely reported as being faster in practice than its alternatives. As Tsukiyama et al. Showed, it is also possible to list all maximal cliques in a graph in an amount of time that is polynomial per generated clique. An algorithm such as theirs in which the running time depends on the output size is known as an output-sensitive algorithm. Their algorithm is based on the following two observations: relating the maximal cliques of the given graph G to the maximal cliques of a graph G, V formed by removing an arbitrary vertex V from G. For every maximal clique C of G, V, either C continues to form a maximal clique in G, or C, V, forms a maximal clique in G. Therefore, G has at least as many maximal cliques as G, V does. Each maximal clique in G that does not contain V is a maximal clique in G, V, and each maximal clique in G that does contain V can be formed from a maximal clique C in G, V by adding V and removing the non-neighbors of E from C. Using these observations they can generate all maximal cliques in G by a recursive algorithm that, for each maximal clique C in G, V, outputs C and the clique formed by adding V to C and removing the non-neighbors of E. However, some cliques of G may be generated in this way from more than one parent clique of G, V. So they eliminate duplicates by outputting a clique in G only when its parent in G, V is lexicographically maximum among all possible parent cliques. On the basis of this principle, they show that all maximal cliques in G may be generated in time O per clique, where M is the number of edges in G and N is the number of vertices. Chiba and Nishizaki improve this to O per clique, where A is the arboricity of the given graph. Makino and Uno provide an alternative output-sensitive algorithm based on fast matrix multiplication, and Johnson and Yannakakis show that it is even possible to list all maximal cliques in lexicographic order with polynomial delay per clique, although the reverse of this order is NP hard to generate. On the basis of this result, it is possible to list all maximal cliques in polynomial time. For families of graphs in which the number of cliques is polynomially bounded, these families include chordal graphs, complete graphs, triangle-free graphs, interval graphs, graphs of bounded boxicity, and planar graphs. In particular, the planar graphs, and more generally, any family of graphs that is both sparse and closed under the operation of taking subgraphs, have O cliques, of at most constant size, that can be listed in linear time. Finding maximum cliques in arbitrary graphs, it is possible to find the maximum clique, or the clique number, of an arbitrary n-vertex graph in time O equals O by using one of the algorithms described above to list all maximal cliques in the graph and returning the largest one. However, for this variant of the clique problem, better worst-case time bounds are possible. The algorithm of Tarjan and Trojanowski solves this problem in time O=0. It is a recursive backtracking scheme similar to that of the Bronker-Bosch algorithm, but is able to eliminate some recursive calls when it can be shown that some other combination of vertices not used in the call is guaranteed to lead to a solution at least as good. Gian improved this to O=0. Robson improved this to O=0 time, at the expense of greater space usage, by a similar backtracking scheme with a more complicated case analysis, together with a dynamic programming technique in which the optimal solution is pre-computed for all small connected subgraphs of the complement graph, and these partial solutions are used to shortcut the backtracking recursion. The fastest algorithm known today is due to Robson, which runs in time O=0. There has also been extensive research on heuristic algorithms for solving maximum clique problems without worst-case runtime guarantees, based on methods including branch and bound, local search, greedy algorithms, and constraint programming. Non-standard computing methodologies for finding cliques include DNA computing and adiabatic quantum computation. The maximum clique problem was the subject of an implementation challenge sponsored by DIMACS in 1992-1993, and a collection of graphs used as benchmarks for the challenge is publicly available. Special classes of graphs, planar graphs, and other families of sparse graphs, have been discussed above. They have linearly many maximal cliques, of bounded size, that can be listed in linear time. In particular, for planar graphs, any clique can have at most 4 vertices, by Kuratowski's theorem. Perfect graphs are defined by the properties that their clique number equals their chromatic number, and that this equality holds also in each of their induced subgraphs. For perfect graphs, it is possible to find a maximum clique in polynomial time, using an algorithm based on semi-definite programming. However, this method is complex and non-combinatorial, and specialized clique-finding algorithms have been developed for many subclasses of perfect graphs. In the complement graphs of bipartite graphs, Koenig's theorem allows the maximum clique problem to be solved using techniques for matching. In another class of perfect graphs, the permutation graphs, a maximum clique is a longest decreasing subsequence of the permutation defining the graph and can be found using known algorithms for the longest decreasing subsequence problem. In caudal graphs, the maximal cliques are a subset of the n cliques formed as part of an elimination ordering. In some cases, these algorithms can be extended to other, non-perfect, classes of graphs as well. For instance, in a circle graph, the neighborhood of each vertex is a permutation graph. So a maximum clique in a circle graph can be found by applying the permutation graph algorithm to each neighborhood. Similarly, in a unit disk graph, there is a polynomial time algorithm for maximum cliques based on applying the algorithm for complements of bipartite graphs to shared neighborhoods of pairs of vertices. The algorithmic problem of finding a maximum clique in a random graph drawn from the Erdos acute NYI model was suggested by Karp. It has been shown that a maximum clique in a random graph can be computed in expected 2O time, although the clique number of such graphs is very close to 2 log 2n. Simple greedy algorithms as well as more sophisticated randomized approximation techniques only find cliques with size log 2n, and the number of maximal cliques in such graphs is with high probability exponential in log 2n, preventing a polynomial time solution that lists all of them. Because of the difficulty of this problem, several authors have investigated the planted clique problem, the clique problem on random graphs that have been augmented by adding large cliques. While spectral methods and semi-definite programming can detect hidden cliques of size omega, No polynomial time algorithms are currently known to detect those of size approximation algorithms. Several authors have considered approximation algorithms that attempt to find a clique or independent set that, although not maximum, has size as close to the maximum as can be found in polynomial time. Although much of this work has focused on independent sets in sparse graphs, a case that does not make sense for the complementary clique problem, there has also been work on approximation algorithms that do not use such sparsity assumptions. Thore describes a polynomial time algorithm that finds a clique of size omega-2 in any graph that has clique number omega for any constant k. By combining this algorithm to find cliques in graphs with clique numbers between n log n and n log 3n with a different algorithm of Bopanna and Haldorsen to find cliques in graphs with higher clique numbers, and choosing a two-vertex clique if both algorithms fail to find anything. Thore provides an approximation algorithm that finds a clique with a number of vertices within a factor of 0.2 log 3n of the maximum. Although the approximation ratio of this algorithm is weak, it is the best known to date, and the results on hardness of approximation described below suggest that there can be no approximation algorithm with an approximation ratio significantly less than linear.